thanks a lot for being here. So I'm very happy to be here to talk about the usefulness of mobile terrestrial LiDAR in silviculture. And I will emphasize my talk on accurate DBH estimation. And I want also to thank my co-authors, the co-authors of this presentation, Rebecca Cordero Montoya and Pascal Rochon. Okay, so in the last decade, there have been a lot of new technology that have been developed to support the study of ecosystems and of forest ecosystems, especially. And at this time, most of these technology have been used to help at the landscape scale or at the tree or plot scales. But there have been limited technology for the study at the stand scale. And it seems that probably the mobile LiDAR technique can be useful to have a better precision at the stand scale, a better description of stand scale. So, and for those who are not aware of what is mobile terrestrial LiDAR, I'll show you in a few minutes. I'll show you right away. So from now on, I'll just say mobile LiDAR. It will be shorter. So mobile LiDAR is like quite simple at first. So what you need to do use the mobile LiDAR technique, you need someone with equipped with a LiDAR sensor that walks into a forest. Simply walk into a forest following a path like that. So this is quite simple. And during that, the sensor captures a lot of data. So you can imagine that there's like thousands of pictures that are taken of points that are taken by the sensor during the walk. So after the walk, you have to make sense of all that. And how do you make sense of all that? You do it with what we call, that's very annoying here. Okay, with what we call simultaneous localization and mapping, and this is what we call a SLAM. Can I hide that? It's very, very. Sorry, I'm very annoyed by this. Okay, and
if you have multiple screens, I was able to drag it over to another screen on my computer.
Yeah, but usually it works, but
okay.
No, it does not. So anyway, okay. So what you do, you need a SLAM algorithm, and what does a SLAM algorithm is that while you walk in the forest, the sensor captures all the objects and localize them and map them all at the same time. So you get at the end a map, a 3D map of your stand from the ground. Okay, so it's very interesting, and the SLAM process is at the heart of the whole approach of mobile LiDAR. Sorry for that. Okay, but there are pros and cons to a mobile LiDAR. For the pros, it's fast. Like you can map a stand 1 to 2 hectares per day, depending of the complexity of the stand, and depending also of your needs. Going on with the pros, you have lower abstraction with mobile LiDAR than with a static LiDAR, and it's more precise to get a sub-canopy description than with airborne LiDAR. Among the cons, it produces heavy data set, and the point clouds, and this is what I want to insist on, are the point clouds are very blurry. So I want to insist on that during that presentation, because I think this is the main limitation to its use in forest ecology and silviculture. So what do I mean by blurry? So let's take this tree here that has been identified through the mobile LiDAR. It seems quite clear, but when we focus on it, we can see that it's becoming more noisy. And you can see when we look at it from above, here it's even more noisy. You have like a donut shape, and if you want to evaluate the diameter of this tree, you don't know if you should measure it from here to here or from here to here. And that blurriness comes from the SLAM process I just explained. It's not that the SLAM process is not good, it's not perfect. So it does not place all the points very completely precisely. So, and the consequences of that, if you want to estimate the DBH of trees, it may get complicated, because here we have some previous results we've got. You have the DBH of trees we measured in the field, and DBH we measured with the LiDAR. And you can see the relationship is not that bad, but for small trees, it's really not good, because if you have, let's say, a 5 centimeter tree with LiDAR, it could in fact be a 20 or 25 centimeter tree in the field. So it's not very useful for further use. So our solution to that is that I think it's quite simple. So we still have that slice here, and we realized that through a series of filters, we could isolate the arcs that forms that slice here. So these arcs are like an image taken, a snapshot taken by the sensor at a very precise time. And there is no noise on these arcs. So it means that each isolated arc can be used to estimate the DBH of the trees by measuring the distance between the most distant points on the arcs. So you can get multiple DBH estimation for a single tree. So what it means is that, let's say here we have 10 selected trees, and we have the estimated DBH and the box plot. And the box plot comes from the arcs that I just explained. So for example, here you have, for tree number 1, you have a quintile 25, the median, and the quintile 75, and so on. You can even see that tree number 8 can be a little bit problematic, and we will come back on that a little bit later. And so these, now we have that, we can look at if the metrics like the median can be used to estimate tree DBH that we got from the field. So when we look at that relationship, we see that the relationship between the DBH based on the median or the DBH based on quintile 75 are very good estimators of the DBH in the field. In fact, we have an R-square almost of 1. And probably that this one with quintile 75 is a little bit better because the slope is closer to 1. What is very interesting in these graphs is that we get a very good estimation of a small tree of saplings. So even below 10 centimeters, we still have a good estimation of tree DBH. So it's very important. It's game changing because it changes completely what we can do with the mobile LiDAR approach. This said, it is not perfect. And for example, here you have a tree with a branch that fell from it, but leans on the trunk. And so if you measure the tree automatically, you will get a measure of 48 centimeter DBH. While in fact, this tree has more like a 32 centimeter DBH. So it's visual validation remains a necessity. You cannot just go and do things automatically and think everything is okay. So what do we learn from all that? We learned that, okay, as I said, we can get very accurate DBH estimations for saplings. But we also learned that that method was only possible to develop because we went through a close examination of the point clouds. We also learned that even though we have a good estimation of most of the tree, we still have to go through a close examination of the point clouds to validate the DBH estimations. And we think that we'll have to go to the same process for other attributes like downwoody debris or tree taper. Okay, so, but now that we know that we can get very, very precise metrics with the mobile LiDAR, it opens the door to new possibilities. And for example, in my lab, we're starting a project in which we're studying beach sapling dynamics. And for example, what we're trying to do is for example, we have a little plot here. We want to know what the probability to have a beach sapling here as a function of canopy opening and the DBH and distance of parent tree. So we can make spatial analysis at the stand scale, this kind of analysis was not possible before the use of mobile LiDAR. So I hope that in this presentation, I convince you that mobile LiDAR is very powerful for studies at the stand scale. But I also hope that I convince you that mobile LiDAR is not a plug-and-play tool. Visual inspection will always be necessary for both its development and use. Thank you.
Thank you all to be here, and yes, we'll speak a bit about how with LiDAR maybe we can better understand agroforest. And to give first a bit of context, we know we have strong issues with agroforest because we are losing them, we are fragmenting them, with an example here near the Biogeoclimatic Lake in Quebec. And this is mostly due to human activities, in particular the forest harvest, because we harvest a bird forest at a rate which is far higher than fire cycles. And also the patterns of forest harvesting are very different to that of wildfires because, as you can see here on the animation, they create remnant patches which are insulated within younger forest matrix. And in addition, something we don't consider that much right now is that also forest harvesting that doesn't target all agroforest. We focus on the most productive agroforest, meaning that often in remnant old-growth landscape will be another representation of poor or disturbed old-growth forest, and it's very different to what we would observe in a natural area. And also another issue is that now we try to protect old-growth forests, but still often our vision of old-growth forests is maybe a bit too reductive. For example, in forest management, we often use what we can name pragmatic definition, meaning that, for example, in the black spruce native forest in Quebec, we consider that all forests older than 100 years are old growth. And we know that, in fact, it's not sufficient because old growth forests, they're changing forests. They're changing in time. They're changing depending on the different histories. They're changing depending on the environment. And it means that within the same old growth landscape, we can have very, very different old growth forests because they don't have the same age, but also because they have different lives with different disturbance and resilient dynamics. And this means that within a growth landscape, we have a wide diversity of habitat and functions at the some scale. And so it's not necessarily the status of old growth forests which explain the ecological importance of growth forests, but rather the internal diversity. And this internal diversity is actually currently not identified by routine surveys. For example, in Quebec, with first survey made by photo interpretation, we observed in recent study that all agroforests in the landscape were classified as regular, even edge, even when most of the forests were several centuries old, irregular, and even edge, meaning that we are underestimating this complexity of agroforests. And this is why in the last years, I started to work with LiDAR to find if maybe we can use this tool to better understand the diversity of agroforest, because there are already different studies trying to identify agroforests within a managed matrix, to define growth indexes, or to estimate the standard of forest. However, the question of the internal diversity of agroforests is rarely taken into account, and even less in rural landscapes, because there are very few research using LiDAR in for agroforest. And so here I represent you shortly the result of two different approaches of the question. One, which is more structure-based classification, when we try to differentiate agroforests with different primary and secondary disturbances history in mixed forest. And the second one, which is more section-based classification, where we try to differentiate agroforests of different edges in the coniferous forest. And these two approaches have common methodologies. First, we use a spatial unit of 1 hectare. And for the metrics, we use canopy height model rather than the raw LiDAR point clouds. And it was because the canopy height model were free and open access, so it's easier to spread the methodology on a larger scale. And in addition, we considered that if canopy height model were already processed enough to identify this diversity of forests, it was unnecessary to use heavier and costly data. Then for the data matrix, we favor a small set of LiDAR displaying vertical structure of forest, or the 99% tree height, the rumper, also named rugosity, the symmetry index, or over the defining the horizontal structure of a forest, such as the gap correction, or the gap, the heterogeneity of gaps within the tile. Just for remixed forests, we also use complementing metrics derived from satellite images, because of the presence of house species and the specific distance dynamics. So here we computed the NDVI and also the mean and standard biannual DNVR computed for the last 30 years to reconstruct the distance history of the forest on the last decades. And for analysis, I've just present the result of classification and prediction based on random forest models, either binomial or multinomial, depending on the study. So for structure-based classification, we chose to do this in the Mont-Valin National Park in Quebec, because there are still a lot of agroforests here, even if we are around, I would say, disturbed areas. And here, the threshold, the official threshold is above 80 years, which is a rather large age threshold. And an issue with this forest is that tree age is a very, very poor indicator of forest age, meaning that we have access to very few data, because in this forest, limited by balsam tree, when you sample balsam tree, but won't tell you the true age of the forest. Balsam tree will be very, very young, even in very old forest. And also, this area are driven by mixed severity regime, in particular spruce bottom outbreaks, which is a disturbance which occurs around all the 40 years, and which severity is very variable within the landscape, meaning that in the same area, you can have big patches of high severity, and just nearby, you can have almost no severity caused by the insect. And so using outlier maps, this outbreaks map, and harvest map, we identify 3 growth classes, so early growth forests burnt 90 years ago, later growth forests unburnt since at least 130 years, and disturbed later growth forests unburnt since at least 130 years, but severely disturbed by the last spruce bottom outbreaks 40 years ago. And we also considered in our analysis the second forest harvested at the same period by the last spruce bottom outbreak, to see if there was similarity between these two classes. And what we obtained was a model with high classification accuracy, above 80%, which was particularly efficient to identify second growth forests, early growth forests, and later growth forests. And in fact, most of the errors were observed for disturbed later growth forests with an accuracy below 50%. And this is due to the existence of an intermediate growth structures we can name the lightly disturbed later growth forest, because we can see that there are evidence of gaps in this forest. So there are forests that have been disturbed by the last spruce outbreaks, but not that severely disturbed. So we create a structure which is between later growth forest and disturbed later growth forest. And I think this is a very interesting result because it can, here we can cultivate Peter Bob Cross, saying that sometimes when you try to classify orographic structures with LiDAR, when you have some errors, maybe they are not errors per se, but maybe a happy little accident showing you something that wasn't identified before. Because what was very likely is after the last program outbreaks, rather than drawing small polygons for each gaps within the studio area, they prefer to draw broad polygons, saying that here disturbance severity was high, while in fact it was more complex within the old growth area. Then for the section-based classification, we are here in near the Père Lake in Quebec, so where I showed the animation before. And here we consider that all forests are old growth when they exceed 100 years. And we chose this area because what was interesting here is that we have a reference of the earlier growth stage with a fire that burnt around 115 years ago. And also we have nearby 2 protected areas unburned since at least 250 years. And also, even if they have been harvested in this area here in purple, there are still many old growth forests of unknown age in the area, so unburned since at least 150 years. And so it was a perfect area to test our model. So what we did, it was we use one of the model to try to classify between early and later growth forests, and but we use this model to predict the succession stage of the old growth forest of unknown age with 3 classes based on the probability of type to be classified as later growth forest. So earlier growth, transition old growth as an intermediate class, and later growth forest. And what we obtained was a model with very high accuracy, about 95%, meaning that using LiDAR data, it's very easy to discriminate between early and later growth forests. And this is a strong improvement compared to a current forest survey, because as I said in the introduction, if we use current forest survey data, almost all the studio area is classified as older than 100 years, but regular and even age, even for forests which are several centuries years old. And for prediction, we were able, with this model, to identify large blocks of late old growth forest located within the matrix of earlier growth forest. And this way, we identify more than 70,000 hectares of old growth forests which are likely to be older than 250 years old. And that's very interesting because it shows you better the internal diversity of old growth forests in the same landscape, here shaped by wildfires of different ages. However, for the predicted transition old growth class, we observe that it was not a succession stage per se, but rather a spatial transition between old growth forests of different ages. So as a conclusion, we can say that LiDAR can be a very powerful tool to provide a finer vision of old growth internal diversity, because this way we can identify structures based on different primary and secondary disturbance histories. However, a strong issue we observed, and I didn't have the time to present it, is that it's very hard to find reliable field data right now, because if we use common forest surveys, the field plot from common forest survey in Quebec, this data strongly underestimate forest age because of the methodology, because they sample only dominant trees at DBH height, and this means that we have very few field data to calibrate and validate a model, because detailed old growth survey of the true age of the age structure are relatively scarce currently in a rural landscape. But still, we try to move forward with, for example, using our model to try to identify late old growth forests on a larger scale, with here preliminary results in the black spruce forest of Quebec, where you can try maybe to identify the last tracts of the oldest of the old growth forests in still primary areas. Also, we try to combine structure and succession to try to identify very old growth forests, severely disturbed by secondary somewhat recently or not. And also, we try to predict old growth features with more details, so try predicting the deadwood volume and diversity, or predicting the amount of soil carbon in old growth forests. So to finish, I want to thank all the partners who helped to fund this project. And if you have any questions, they're welcome. Thank you.
Hi, everyone. I'm Lucas, and I'm excited to talk to you all today about our study on ground noise filtering when modeling above ground biomass with LiDAR data. So quick introduction on myself. I'm a PhD candidate at SUNY ESF, and mostly working on mapping forest above ground biomass and carbon with open data across New York State. So a little bit of context. In 2019, New York State passed its landmark climate legislation, the CLCPA, and as part of that, the state and our group are working to hit net zero emissions statewide by 2050. So a huge part of this is, of course, reducing emissions through renewable energy sources, but acknowledging that there are parts of the economy that really won't be able to decarbonize in the next 30 years quite as quickly. We need to make up that difference, and we're looking to manage our lands and forests so they're continually sequestering carbon, at least the same amount that we're releasing. But in order to manage carbon sequestered in our lands and forests, we first have to measure that across the state, and that's no small task given how large New York State is. So we're pretty lucky to have a rich forest inventory data set. It's collected by the U.S. Department of Agriculture with their Forest Inventory and Analysis, the FIA program. And so roughly 5,000 plots are measured every year. And this is an invaluable data source, but these plots cover relatively small footprints, and they're only measured on a rolling 7-year basis. So really this data is meant for county and statewide level predictions, which makes it challenging when you want to predict forest biomass at a local scale for active management or for monitoring sequestration rates. So a lot of groups have filled in gaps between these plots with LiDAR data, and based on the context in some of these talks, I'm pretty sure everyone's pretty familiar with LiDAR, but in our case, we're using airborne LiDAR, which essentially collects height measurements from a laser sensor that's attached to a plane. And in this data, we can collect tree height measurements over a much larger extent, much cheaper and faster than what we could do if we were measuring trees on the ground. So we compute summary statistics describing these point clouds, so you can get a sense of what a site might look like on the ground. And if we couple these variables with FIA measurements, we can then build models to extrapolate the FIA biomass outside of the areas that the Forest Service has actually measured. And there's been a bunch of success with this area-based approach through most of New England, Maryland, and Pennsylvania, and regions in the Pacific Northwest of the United States. And as luck would have it, in New York State, we've got a pretty large set of recently acquired LiDAR. It covers more than half the state. And over the past couple of years, we've been training models to predict forest biomass using this data. And we've got a preprint of that study, which I can share later. But the first thing we had to do is to compute our summary statistics. So these summary statistics include things like the mean height of our points, the max height, other distributional traits. And what I'm showing here in this slide is essentially a cross-section of some LiDAR that we would include in our models. And the red points are at the highest elevations, and the blue points are at the bottom along the ground. And this slice is continuously forested, and we can corroborate that with imagery. But you'll notice there's still quite a few points that are getting through the canopy and hitting the ground. And so what a lot of other biomass modeling efforts do is they sort of toss out this ground noise in a process that we're calling ground noise filtering. And the idea is pretty straightforward. If you're interested in measuring biomass in trees, and these points are hitting the ground rather than trees, then you might not be interested in these points. But we sort of chased up a citation chain to see why people were doing this, and we realized that no one had actually investigated how this actually impacts biomass models. So a lot of biomass modeling studies cited other biomass modeling studies, and it really goes back to a few studies from the late 90s that introduced this practice. You have Mats Nielsen in '96 used helicopter-borne LiDAR to estimate tree heights. And he set any points below 2 meters to 0. And another study modeling tree heights, NAFEW, in 1997, threw out points below 2 meters. So the idea being that if you're measuring tree heights, you know, that makes a lot of sense. Those points below 2 meters aren't going to be representative of a maximum tree height. So at some point, the field moved from modeling tree heights to biomass. And this process of filtering ground noise has sort of stuck around. But you know, the way we're thinking about it, when you're estimating the biomass of a stand, it might be useful to know how much of the stand is open enough that these laser pulses can actually get through the canopy and hit the ground. So the amount of unoccupied space in this sense might be just as relevant as the size of the trees themselves. So our first objective that we set out to explore was whether or not ground noise filtering actually improves biomass models. And again, the LiDAR data we have spans a number of different regions. And a lot of New York State is post-agricultural, with cropland starting to return to forest. And you can see sort of a cropland band running east to west across the center of the state. And then at the same time, we have the Adirondack Park in the north, which is the largest protected area in the lower 48 United States. So we've got quite a range of landscapes represented here. And that brings us to the second objective, which is to identify if impacts of filtering were associated with any landscape metrics defined by LCMAP land cover classes. So if ground noise is helping us identify more open stands and empty spaces, we wondered if ground noise filtering would have a bigger impact in patchier and less forested landscapes. So we filtered our LiDAR data 4 different ways, removing points at 0 meters and below, points 1 meter and below, or sorry, 0.1 meter and below, so 10 centimeters and below, and then 1 meter and 2 meter thresholds. And we fit random forests to each of these data sets, plus the original unfiltered data set. And we used an automated approach, an automated machine learning approach to tune each of these models to make sure that we didn't have, you know, our finger on the scale in any way, biasing one model and data set over the other. And then we compared the performance of all of these models against each other, both statewide and in relation to landscape metrics like patchiness and forest cover. And perhaps not surprisingly, we found that truncating our data by getting rid of these lowest sets of points was highly impactful to our variable distributions. And what I'm showing here is a selection of variables, predictors, that we included in our models. And as you can see, there's quite a bit of movement between our unfiltered control data set in the gray and the various filtering threshold data sets with different colors. And maybe also expected the difference between our unfiltered predictors and the filtered predictors gets larger as the intensity of the filtering increases as we use higher and higher thresholds. So really the kurtosis of these variables increases, and what we're seeing and what we're saying is that we're reducing the amount of information available to our models when we filter this way. So we fit our models to these predictor sets, and we assessed their accuracy against FIA measurements through leave one out cross-validation. And we found that across New York State, our models generally got worse the more intensively we filtered, with error metrics like mean absolute error and root mean squared error increasing with filtering, and agreement metrics like R squared decreasing with higher and higher filtering thresholds. And there's one exception here, and that's that our models were at their least accurate at this 10 centimeter filtering threshold. And we don't have a great explanation for that. But what we can say is that generally the unfiltered model was consistently the most accurate for New York, and that filtering decreased our model accuracy overall. So that's our first objective. Ground noise filtering does not help models of forest above ground biomass in this context. And if anything, it hurts it. So our next objective, the second objective, we looked at how changes in accuracy were associated with things like edge density patch density, and forest cover as defined by LCMAP. And to do that, we took each of these LiDAR regions or collections as its own unit and calculated landscape metrics within the boundaries. We also calculated model accuracy within each LiDAR collection border, and investigated how the accuracy changed with different filtering thresholds. So what we found was that, yes, the impacts of filtering are much more notable in the fragmented and less forested coverages. So what I'm showing here in this chart is the change in RMSE for the 1 meter filtering level. So not that strange 10 centimeter level, but the next higher one. And higher RMSEs mean more of an impact from filtering. And what we found is that fragmentation metrics like edge density and patch density were generally positively correlated with RMSE. So patchier landscapes were more impacted by filtering overall. And similarly, areas with less forest cover were more impacted by the models as well. So something interesting here is that the most forested and least patchy coverages, we actually see that filtering had almost zero impact or sometimes a slight benefit. And you can see that with a couple of these points at the bottom of these charts. So one caveat, maybe if you're only interested in mapping a contiguously forested area, ground noise filtering might help improve your models by a bit. But these improvements are quite small and not guaranteed. So what we think is that filtering should really be a careful decision and not the sort of standard pre-processing procedure that it seems to have become. So to wrap up some takeaways here, we found that filtering out the lowest points from your LiDAR data doesn't help and often hurts models of forest above ground biomass. And in particular, it tends to hurt patchier landscapes, which are often the things that are being, or the kinds of landscapes that are being modeled in more recent wall-to-wall, statewide, region-wide mapping studies. So we recommend that if you're looking to build these sorts of models, that you don't filter your data unless you've got a very good reason or unless you can test it out like we've done here. So that's my time. I can share a few links to preprints for this study and our biomass modeling study in the Zoom chat. And thanks everyone for listening.
Shay Alkin is our next speaker from University of Northern British Columbia. Title of Shay's talk is Evaluating Forest Growth Potential Using Airborne Laser Scanning Derived Biogeoclimatic Ecosystem Classification Models. And so I'll hand it
That's
off.
great, Adam. Thanks very much. Welcome, everyone. Thanks very much for sticking around on the later part of the last day of the conference here. What I'm actually going to be presenting today is a subcomponent of a broader project that we're doing out in DC here that's looking at using airborne laser scanning to create predictive ecosystem maps. And specifically what I'll be talking to you about is work that one of my master's students did, Louise Terrazan, who is asking the question, can we actually get better estimates about how our forests are growing using the same similar type of modeling framework? Now, throughout this conference, there's been some great sessions, great presentations on what we need to do, adaptive silviculture for climate change, ecological silviculture. A lot of the focus is on managing for complexity and kind of managing for heterogeneity within our forest landscapes. And I think one thing that's really sitting in the background of a lot of this new development is that we obviously want to try to map on our silviculture decisions, our forest management decisions, onto where in the landscape they're going to have the biggest impact and where they're going to be the most beneficial. Now, this obviously isn't new. We've been doing this for a long time. In Western Canada, in BC, the way that this has historically been done has been using what we call the Biogeoclimatic Ecosystem Classification System, or BEC. Now, in this system, we basically break down the province into different biogeoclimatic zones, which are each defined by a dominant forest type. That can then be made finer resolution to bring it down into lower levels, and finally down to actually a site series estimation So for each forest type, we're going to do a classification based basically on where it is within this ecotopic grid, what's its relative soil moisture, what's its relative soil nutrients. And this is what we refer to as a site series map. This is important because it really is the fundamental part of a lot of how we continue to do forestry in BC. It drives our decisions of what we're planting, what type of silviculture is going to be most appropriate where. The other thing it gives us is an estimate of how well those forests are going to grow in the future through our growth potential or our site index estimation, which we historically have termed SciBec. So this is good. This, again, just mapping on our silviculture to what's actually on the landscape, but it is at a fairly coarse scale. The question that we're trying to pursue is whether or not we can use a lot of this emerging technology, such as airborne laser scanning, in order to provide much more accurate estimates of what our actual ecosystems are doing. And that's really been the focus of this bigger project, this predictive ecosystem modeling project. So just to quickly kind of go through the framework there, what we're doing is trying to create these predictive ecosystem maps based on ALS data. So start off, collect the good field data of our site series classification throughout the province. Link that with a range of different landscape layers that are all derived from high resolution DEMs that are taken from the area laser scanning. And then using this in combination, we've been able to produce these high resolution landscape scale maps of what our BEC system site series are. So that's nice. It actually produces really some important operational maps that we're starting to use to inform our management decisions. The question remains, though, can we actually get better estimates of what the actual growth potential will be on these sites by using a very similar framework? So can we estimate site index using similar ALS-derived layers? And that was kind of the question that we were going after here. Specifically, we wanted to look at three aspects. So first, can accurate growth potential models be developed from this type of ALS PEM data? Secondly, does the model accuracy and applicability actually vary between ecosystems? So we're going to look at across a range of different forest ecosystems and ask whether or not we can use it only in some or in others that we can't. And then finally, if we are actually applying it to a range of different forest types, are there actually different predictor variables that are needed in order to get those accurate growth potential models, given that we kind of assume that the growth limiting factors in one area may be different than the primary growth limiting factors in another area. So to approach this, we tried to develop these type of techniques in 3 different case study regions that were kind of spread throughout BC and Western Canada. Now, I'll just spend a little bit of time talking about the forest types that we were using here to give you an idea about where the model's being fit. So to begin with, in the northwest part of the province at our Deception Lake field site, this is an area that at higher elevations dominated by Engelmann spruce, subalpine fir. Once you get down to lower elevations, it's primarily subboreal spruce. And as you can see in this photo on the top right here, it's a very mountainous region, lots of topographic complexity. It's also an area that gets a considerable amount of precipitation, so we deem it as being a moist area, not wet, but just moist. And it is quite cold, so cold really is a key factor. From there, we can go to our second case study site, which is in the central interior of the northern part of BC at our Eliza Lake Research Forest. Here, this is in the subboreal spruce forest conditions. And because we're in the central interior plateau, it's actually a very flat area. So as you can see in this bottom right figure here, not a lot of topography, really flat. It also gets a lot of precipitation and it's relatively cool. Not as cold as Deception, but relatively cool. So flat, wet, and cold is how we'd characterize the Eliza Lake. And then we drop down south to a case study site called Eagle Hills. Here again, we're in the central interior. It's in the interior Douglas fir BEC zone. It's an area that's not mountainous, but it's not flat. It's kind of defined by this hilly landscape. The key thing, though, is it's very dry and warm. So giving rise to Doug fir forest, giving rise to good growth for lodgepole pine. So using this framework, what we want to do is ask, can we actually get better growth potential estimates using ALS data. And to do this, what Louise and his team did was go out and actually get empirical estimates of the site index by going out and sampling even-aged plantations that were in the 10 to 30-year-old range. And we did this to try to make sure that our empirical estimates of site index were actually as accurate as possible by sampling these even-aged sites. When Louise was doing his sampling, he really wanted to make sure that he was sampling across a range of different topographic features and was covering the full extent of each of the case study regions, which is kind of shown in the right here. Now, once he had this good empirical data in hand, needed to pair it with the aerial laser scanning data. And from the aerial laser scanning data, importantly, what we were only really using was the high resolution DEMs that we were able to derive from that. And this is important because we're not taking into account any of the vegetation structure. It really is just what is the impact of these landscape features on growth potential. So we derived a range of different other terrain attribute layers from this, going from simple things like aspect and slope up into a range of different topographic indices or terrain layers that really reflect where these sites are within the landscape using various different metrics. Now, once we had this, the real test was comparing or figuring out how best we could actually estimate site index. And we actually tested 3 different models or 3 different pathways for getting a site index estimation. So in the first model type that we tried here, we were using the ALS data, but here actually using our tree height estimates from ALS, pairing that with information on tree age, and then just doing the normal thing that we do to get site index, going through using site growth index growth curves in order to get our site index estimate, what I'll be referring to as a tree height model. So that's kind of the classic way that we go through and get our site index. Here, just using ALS instead of going out in the field and actually measuring tree heights. The second framework that we wanted to compare was, again, using the ALS data, but here just using those DEM-derived variables. So not using anything about tree height, only using the landscape features. From those landscape features, we created a model to predict the site series, the predictive ecosystem map, which resulted in our site series estimation. And then once we had that site series estimation, we could then feed that data into our SciBec model in order to get a site index estimation. So what I'll call the PEM SciBec model. Now the third framework was going directly from the aerial laser scanning and the DEM derived layers and using them to directly create models of the site index, which I'm going to refer to as the PEM ALS models. So what did we find? Well, the first thing that we can look at here is how these 3 different model types for estimating site index performed in one of the case studies. Here I'm going to show the Eliza Lake case study in the central interior, but basically got the very similar results at the other 2 as well. So to start with, starting at the top here, this is the tree height model. And you can notice that it was giving us our best results in terms of estimating site index. So an R-squared value of 0.55. Now, one thing I'll note there is that that 0.5 R-squared value doesn't reflect the fact that we were not getting good height estimates. If we actually just look at the R-squared value using our area-based approach for getting tree height, it was in the 0.87, 0.9 range, kind of what you'd expect. LiDAR should be really good at giving us these tree heights. Why our R-squared drops down here for the site index is actually the uncertainty that we actually have associated with our age estimations. So it was a combination of that age uncertainty that really brought down those R-squared values there. But it still was the best model overall. We can go from that best model into the worst model, which was this framework where we're using the ALS data to predict the site series, and then going from the site series to our site index through the SciBec. Now here, a really important thing to clarify is that we actually have a lot of confidence in our site series estimation. We're able to say what the actual vegetation is, what the type of forest condition is quite well. Where this model seems to fall down is actually in the transition from that site series estimation into the site index estimation through SciVec. And that's kind of shown here by the fact that if we look at these points, the SciVec model really only predicts 2 different site index differences across a whole range of the site series. So not doing well, but it's not doing well because we're not predicting the site series. It's doing not too good because of the SciVec submodel. And then finally from that can go into this final modeling framework that we're comparing, where here we're getting not a bad R-squared, 0.38. And this is where we're using those landscape level derived layers to actually directly estimate the site index. So lower than what we got in our tree height model, but there's a big, big caveat in that this model can be applied anywhere. It's not contingent on actually having good estimates of tree age. You must have tree age estimates in order to use the tree height model. So take home here is we can do fairly well at getting these fine-grained landscape level estimates of site index using this similar framework. We can then kick into the question of, do we actually see similar results across these 3 very different ecoregions? So here, just showing the overall results for our central interior site, the flat, wet, our southern site, Eagle Hills, the very dry, warm area, and our cold, topographically complex and wet site at Deception. And if you look at the top number here, which is our R-squared from our leave one out cross-validation, you'll notice that the values are all very similar across the 3 regions. So going from a 0.38 at the flat, wet site to a 0.43 in our dry, warm site. So it basically, it can work across the different regions. There's no hard caveat that you can only apply this in really flat landscapes or in really dry landscapes. It still works. The other thing I'll just quickly mention is that our leave one out R-squareds are really not that good. But if you just look at the pure correlations between our predicted and our empirical data here, we're getting values that kind of more correspond to what our eye is looking at when we look at these regressions. Now, the last question we want to address was, do you actually need to use different predictor variables in these very different forest ecosystems? So I won't go through this in detail, but just kind of pull out the main take-home messages. And the main thing that we found was that across these 3 sites that had 3 very different forests that we assume that growth is being limited by different ecological factors, that topographic position variables were important for all of them. So basically variables that tell us something about whether or not a site is going to be water receiving or water shedding. And then the interesting thing here is that these topographic position variables were still the most important variables even in our flat, wet site at Eliza Lake. The last thing I'll just mention here is that if we go to our coldest site, there we did see that these landscape variables that were indicative of how much solar radiation the trees were going to get, and therefore about how much heat, were also good predictors of what was going on. So just kind of wrap up, this framework does allow us to produce these high resolution site index models. They should be useful for actually improving where we do different silviculture options. And it seems to be a framework that we can apply across a range of different forest types with the caveat that the exact model structure that will give you best fit is going to differ. And I'll just leave it there if there are any questions.
So as Adam said, I am a research ecologist with the U.S. Forest Service. I'm based out of Anchorage, Alaska. And today I'm going to talk a little bit about some work I did as a postdoc with forest inventory and analysis and the U.S. Forest Service, looking at how or what the contribution is of biotic predictors when we're looking at sort of regional scale models for invasive plants. So as ecologists, I think one of the most fundamental and to me, one of the most interesting questions that we ask is, why do we find a species where we find it? And in the case of invasive species, this is a particularly important question because we know that invasive species can have really devastating impacts on recipient ecosystems. They can really negatively impact or very significantly change disturbance regimes. And they can have really significant monetary impacts as well. millions, if not billions of dollars in lost revenue can be, attributed to really large scale invasions. So being able to predict where environmental conditions favor invasions is really important, and understanding the scale at which different checks on invasions happen can help us better prevent or manage invasions. So when we talk about where a species occurs kind of in the largest possible sense, what we're talking about is its distribution, and sort of a theoretical model that's often cited in terms of understanding what determines a species distribution is this BAM model, or biotic, abiotic, and migration, with the idea being that a species occurs where suitable biotic conditions and abiotic conditions overlap, and that species can migrate to that area. So this is a pretty intuitive idea, nothing too controversial here, but what's far less understood is kind of the spatial scale at which each of these sort of checks on the distribution take place. So in the species distribution modeling literature, there's this paper I just looked this morning, cited almost 4,500 times at this point. So super commonly cited paper that kind of tries to answer this question for distribution modelers by saying that at these sort of large global to landscape and even local scales, really what's determining a species distribution primarily is going to be abiotic conditions, what Hutchinson would have termed xenopoetic. So things that really aren't going to be affected by who's occurring on the ground and sort of the biotic interactions that are happening down there, things like climate and topography, versus biotic interactions, which really are expected to come in kind of more at this local, the micro scale. And Hutchinson would have termed these bionomics. So what a species is experiencing is directly related to how other species are sort of augmenting the environment. And this idea has been cited, like I said, a lot, often in defense of building species distribution models that solely use these xenopoetic type variables, so things like climate and topography, to try and predict where the environment is suitable for a species to occur. And often there's good evidence that that's an okay practice, but there's a growing body of evidence that is showing that actually the signature of biotic interactions on species distributions is really detectable at a much larger scale than we previously recognized. In invasive species, I just put a few examples here. There's really not a whole lot of examples with invasive plants, but there's some evidence that at these really fairly coarse resolutions of regional scales or regional scale models, we can detect the influence of land cover at like a 2 to 10 kilometer resolution in these models, and they can actually improve the models when you include land cover. But sort of on the flip side, on the other hand, there's also evidence that at least for this invasive grass species that's shown over here on the right, the authors of this 2014 paper really didn't find any signature of interspecific competition when they're building regional scale models for that invasive grass. So this question is really still very much up in the air regarding, well, what's the role of biotic interactions when building these regional scale models, at the resolutions that are typical of those models. And specifically for invasive species, and invasive plants in particular, we really just don't have that many studies. So kind of getting at this type of question was the goal of this research. And we are setting out to answer two fairly simple questions. The first simply being, do biotic predictors significantly improve regional scale models for invasive species distributions? And then the second being, if Pearson and Dawson kind of have it right, that their influence declines as you sort of increase your spatial scale and decrease your resolution, do we see that the contribution of these biotic predictors to model fit really decreases with that decreasing resolution? So to get at these questions, we use data from the Forest Service Forest Inventory and Analysis data set, which Lucas mentioned earlier. I won't go too much into it, but we used a network of plots throughout California, Oregon, and Washington, about 10,800 plots. So we have a really good sort of spatial coverage in forests throughout the region. And that's somewhat unique to this study. It's the first of which I'm aware that specifically looked in forested systems at invasive species. And what we did is throughout this network of plots, we looked for presence or absence of 5 really common invasive species. So we've got 3 bromus species here, Tectorum, Diandrus, and Hordiaceus, 1 forb, Hypericum perforatum, or St. John's wort, and then 1 shrub, Rubus armeniacus, or Himalayan blackberry. So using that understory data that's collected as part of this plot network, we can say, is the species present? And I should say the caveat here is at or above 3% cover. So we're calling this the presence of an infestation rather than a simple presence absence. Or is there no record of that species, which we're calling an absence of an infestation? And what we can do then is pair those presence absence data with predictors that we kind of chunked out into 2 main categories. Sort of an abiotic and disturbance are sort of xenopoetic, although disturbance is obviously influenced by what's going on the ground. So we'll just call it abiotic and disturbance predictors. So things like topography, bioclimate, and the fire history of the area. And then biotic variables. So things that are kind of describing competition with the existing forest in that area. So basal area of live trees, canopy cover, stand diameter, and stand age, and then the variation in each of those. To kind of get at the question of how this can change with changing resolution, we built these species distribution models, ensemble models, using 4 different algorithms at 5 different spatial resolutions. So pixel sizes, I might sort of swap between those 2 terms, but when I talk about resolution, I'm talking about a pixel size. And in this case, we had a 1 by 1 kilometer pixel, 2 by 2 kilometer pixels, 3 by 3, 5 by 5, 10 by 10. So decreasing resolutions. And we also built these models using just the abiotic and disturbance predictors. So what I'm going to be calling the abiotic model from here on out, and then all possible predictors. So abiotic, disturbance, and biotic. And I should say, we use the same number of predictors in every model. So any changes in model fit are not due to just increasing the number of predictors. It's actually how much the predictors are able to improve the model fit. So after building these ensemble models for each of the 5 species at each of the 5 resolutions, and in the 2 different, or using the 2 different sets of predictors, we then evaluated the model fit according to the true skill statistic, which, if you're not familiar, is in a nutshell just a way to evaluate how well does the model fit. So how well does it do at predicting true presences and true absences. So before I get into the results here, I just kind of want to orient you to what this figure is going to look like. We've got our resolution down here on the x-axis. This is actually decreasing resolution. So 10 is a low resolution, really coarse pixel size. 1 is our highest resolution. And then on the y-axis here, we have delta TSS. So that just means the difference in that true skill statistic, or the difference in model fit between our full model that, remember, included all of the different types of predictors, both abiotic and biotic, and then the fit of our abiotic only model. So basically, this is giving us an idea of how much does the inclusion of biotic predictors actually improve the model, if it does at all. So anything above this 0 line is an improvement by including biotic predictors, and anything below the line means actually including biotic predictors is yielding a worse model. So the first result that I just wanted to highlight is the fact that at 1 kilometer pixel size, these biotic predictors actually did consistently improve model fit. So this was consistent across every species. There was some variability in the degree to which they improved it, but we can say that yes, at a relatively fine pixel scale, when we're talking about a regional model, actually including these biotic predictors does improve the model. And then sort of the second part of that story is that the contribution of these biotic predictors to improving model fit declines significantly as our resolution becomes more and more coarse. So we're still seeing kind of a positive impact, but not significant, from 2 to 3 kilometer pixel sizes. But then as we move towards coarser and coarser resolutions, really no like an overall kind of a negligible impact at a 5 kilometer resolution, and then actually kind of a negative impact at this 10 kilometer resolution or pixel size. So taking all of that, we can then go back to the questions and say, well, yes, biotic predictors did significantly improve these regional scale models, but only at the finest resolution that we observed. So as resolution becomes more and more coarse, these things become less and less informative, which isn't terribly surprising, but it's a good demonstration that the idea that's out there works, and also that maybe we should be considering including these in relatively fine scale resolution models at the regional scale, but maybe it's not something you need to sweat too much when you're using a relatively coarse scale resolution. And we also did see that their contribution to model fit or to improving models did decline with decreasing resolution. So that again kind of sort of supports what Pearson and Dawson were saying, but maybe says, well, we could consider sort of bumping up that threshold where we should, where it's okay to stop using biotic predictors. So they may be acting at more coarse scales than was sort of previously recognized. Okay, I know that time is short here, so I'm going to try and scoot through this last slide. There's a few possible explanations for this. I don't have time to go into every one that we cover in our paper. I'll put the link to the paper in the chat in case anyone's interested in reading more. There's a lot more in the paper than I can cover today. But the first is the ideas underlying the Eltonian noise hypothesis, which basically says that biotic interactions happen at such a fine spatial scale that once you start to kind of aggregate pixel sizes more and more and more as you sort of make the resolution less and less, it sort of just turns into noise and becomes unintelligible and uninformative in these more coarse scale models. So that's one possibility, is that just they became uninformative beyond a 1 kilometer pixel size. And the second is that the types of biotic interactions represented by our predictors were more like a competition type of predictor. It tells us something about maybe competition for light with forest overstories, which we know can be important for invasive species. Many are shade intolerant, but there's some evidence from the literature, not necessarily with plants, but with other invasive species that say, really the biotic interactions that are going to be picked up in these models at relatively coarse resolutions, or that are more likely to, are positive biotic interactions, so mutualisms and things like that. So because ours represent more of a negative interaction, it could be that we're just not picking them up at that resolution. So those are two possibilities. There's others we discuss in the paper, but that's kind of two to highlight. And with that, I'll just thank my collaborator, Andy Gray, on this paper, and all of our phenomenal field crews and database managers that collect all of these data and let us have a lot of fun playing with it.
Thank you for the presentation. It was very interesting.
My name is Davis. I'm coming to y'all from the southeastern United States, specifically Tuscaloosa, Alabama. And today I want to share some of our findings from a recent study where we investigated the impacts and the patterns of intermediate severity wind disturbance in mixed oak pine, specifically shortleaf pine stands in Tennessee. So I'll start kind of by introducing this idea of intermediate severity disturbance. So along the disturbance severity gradient, these intermediate severity disturbances occur between the very frequent localized single tree gap scale disturbance and then the infrequent stand replacing catastrophic severity disturbances. So these are right in the middle on that gradient, and these may result in a high frequency of localized canopy gaps or relatively few large gaps, or some combination of both. And these intermediate severity wind disturbances are really understudied relative to gap scale processes and catastrophic stand replacing disturbances, but they are equally, if not more, influential drivers of forest ecosystem change. It's been determined from recent studies that intermediate severity disturbance events have a shorter return interval than the lifespan of most canopy trees. So most forest ecosystems will likely experience one of these intermediate severity disturbance events in their lifespan. And there's a wide range of intermediate severity disturbance agents, such as ice storms, fires, maybe insect disturbance. But we specifically in this study investigated the impact of wind as the disturbance agent. And you can see in some of the photos here some uprooted and snapped trees that really opened up the canopy. So intermediate severity disturbance may be a necessary component to maintain certain stand species assemblages specifically in the southeastern U.S. Oak pine mixed species stands. Here, wind disturbance is one of the most common canopy disturbance agents. And these oak pine mixed species forests have experienced a rapid decline in their extent, which can largely be attributed to altered disturbance regimes, changes in land use, the proliferation of commercial pine plantations here in the Southeast, and also lack of active management. So in these mixtures, shortleaf pine specifically is one of the most well-suited of the southern yellow pines to co-occur with oaks and other hardwoods, and has a pretty extensive range. You can see the range map from East Texas all the way up north to New Jersey. And our working hypothesis is that intermediate severity disturbance kind of facilitates the establishment and recruitment of compositionally distinct pine patches in what is an otherwise oak or hardwood stand. So the three objectives for this study were to, one, quantify post-wind disturbance species composition structure and also residual tree spatial patterns. Number two, to infer the individual tree, neighborhood, and site-specific impacts on individual tree mortality. And the third one was to describe the frequency, size, shape, and spatial distribution of intermediate severity created canopy openings. So this study occurred in a wind-disturbed forest, mixed oak shortleaf pine forest at Savage Gulf State Natural Area, which is in south central Tennessee on the Cumberland Plateau. You can see in the drone image here, we're up on the tablelands of the plateau, and it falls off into the Gulf there, which is why it's named Savage Gulf. So the forests here are dominated by oaks, specifically white oak, black oak, scarlet oak, and also pine, so shortleaf pine and Virginia pine. And then in the mid-story, red maple and sourwood are abundant. So the specific intermediate severity wind disturbance that we studied occurred in November of 2018, and this was a pretty widespread thunderstorm event that impacted a large portion of central Tennessee with a lot of embedded tornadoes. Specifically, there was one EF1 tornado that dissipated just prior to reaching Savage Gulf. And however, the severe thunderstorms did produce discrete microbursts, and you can see some of that, some of the horizontal downwood in this image here on the right. So for our field methods, we installed an inventory of 32 10th acre, 0.04 hectare circular plots in disturbance impacted shortleaf pine dominated neighborhoods. And on these plots, we sampled coarse-wooded debris, trees, saplings, seedlings, and other abiotic elements. And then for our analytical methods, for the first objective, we used a pair correlation function to quantify a change in tree spatial patterns before and after disturbance. And for the pre-disturbance tree locations, we considered the uprooted and snap trees to be pre-disturbance trees. And then for the second objective, we modeled individual tree disturbance susceptibility with a random forest classification algorithm. And here we wanted to determine the individual tree characteristics and also the spatially explicit neighborhood characteristics that were most influential on the probability of individual tree survival from the wind disturbance event. And then finally, for the final objective, scaling up to the forest scale, we used a pixel-based classification to classify canopy openings using high-resolution images. Unfortunately, we didn't have, I've learned so much from this session about all the different LiDAR techniques, but we didn't have LiDAR data available post-disturbance, so we used multispectral imaging. So the figure here in the middle shows kind of that process going from the true color image classified to the canopy openings here. And then with these detected canopy openings, we use some landscape metrics to quantify the shape, size, and frequency of these. And then we took that a step further and quantified the spatial patterns of the canopy openings with a modified point pattern approach for objects with real shape and finite size. So not taking the midpoint of these openings, but actually taking the edge-to-edge distance and looking at patterns there. So here's some results from the first objective, 3 tables here. The first one is the coarse-wooded debris table. So we have standing coarse-wooded debris basal area and down coarse-wooded debris volume. And we can see that the majority of those were oaks and pines. So Virginia pine, scarlet oak, white oak, shortleaf pine, the canopy dominant trees were the most affected. And then for their actual residual trees, similar trend, we had pines and oaks that had the highest dominance, but in terms of density, red maple and sourwood were the most abundant. And then a similar trend for the seedling and sapling. So red maple American holly and sourwood had the highest density in both the seedling and the sapling layer. And then the figure on the right here shows the spatial pattern analysis. So this is point pattern analysis, the pair correlation function. And so the red line here is the real data, and the gray area is a simulation envelope. So we simulated the real data 99 times under the assumption of complete spatial randomness. So we can interpret this as if this red line appears above the gray envelope, that would be considered significant spatial clustering at a given distance here given on the x-axis. So we can see that going from pre-disturbance trees to post-disturbance residual trees, that the spatial pattern really didn't change much. We might expect a change in spatial patterns after catastrophic disturbance where residuals become either aggregated or dispersed, but we didn't find that after this intermediate severity disturbance. And then here's some results from the second objective, from where we wanted to infer the individual tree and neighborhood scale characteristics that influence survival. So variable importance. On the top left figure, we go from most important to least important. Taxa was the most important, followed by basal area, and then distance to nearest neighbor. And with these three most important predictors, we also estimated partial dependence plots for these to see how each predictor influenced probability of survival. So in the bottom left here, maple and sourwood were found most likely to survive, and the two pine species were least likely to survive. And then looking at probability of survival based on basal area and distance to nearest neighbor, we see a trend that's been well documented. Smaller trees were more likely to survive. Trees from about 30 to 50 centimeters were least likely to survive, and it plateaued with the very large trees. And then trees with a shorter distance to their nearest neighbor were less likely to survive. And then here's some results from that remote sensing analysis. So this is a 174 hectare portion of Savage Gulf, and it's a funny shape because in the northeast corner is a commercial pine plantation, and in the southwest portion of this map is the actual Gulf. So we were up on the tablelands here. So these are the openings that were classified. The blue openings are large openings, those greater than 250 meters squared. And the yellow openings are the smaller ones, less than 250 meters squared, but still greater than 50 meters. So we can visualize those in space here, and then we can actually quantify the spatial patterns. With this figure on the right, it has the exact same interpretation as the pair correlation function we saw a couple of slides back. So we found significant clustering generally at distances less than 150 meters. So these were significantly clustered in space. And then at greater distances, they became randomly distributed. So this means that at distances less than 150 meters, you're more likely to find an opening adjacent to a given opening than you are not. And the random distribution indicates that you're no more or less likely to find an opening at that distance. And then here's the gap size frequency distribution. So number of openings per hectare on the y-axis, and then opening size on the x-axis. A typical reverse J distribution, about two gaps per hectare in the 50 to 100 and 100 to 150 meters squared. We found about one gap per 8 hectares greater than half a hectare in size. So for gaps that were half a hectare in size, there was about one for every 8 hectares. And the biggest gap that we detected, or opening that we detected, was 3/4 of a hectare. And then here's some results from the landscape metrics. So going from top to bottom, large openings had a greater mean distance to their nearest neighbor, had a greater mean shape complexity. Surprisingly, kind of the smaller openings had a greater mean perimeter area ratio. And this is probably because these were single tree openings and as the tree falls in a wind event, it creates more of a elliptical shaped or ellipse shaped opening. So maybe that's why the perimeter area ratio is higher for those. And then obviously this is intuitive, but large openings had a greater mean perimeter and greater area. So what does this mean for management here? So here's a 45 hectare sample of that larger 174 hectare study area. And we can see some large openings and some small openings. If we really want to emulate these patterns of natural canopy disturbance in our silvicultural systems, we can do something like this, where we cluster or enter the stand and create these clusters of openings, relatively large openings, but maybe 2 to 5 of these in one cluster. And in these mixed oak shortleaf pine stands, the pine management is more crucial than maybe the oak management. So these could be like regeneration harvest of oaks. And really what we want to stress with these findings is that pines or any entries in these systems, if you really want to emulate natural disturbance, these entries should be in patches and maybe not uniformly treating the stand, but creating them in patches. So compositionally distinct pine patches in what is otherwise an oak stand. And regardless of whether artificial or natural regeneration is necessary, we want site preparation with prescribed fire. And we found a lot of the residual trees were these big maples and sourwoods that were of a diameter too large to really be controlled by these low intensity prescribed fires. So in some stands where fire has been excluded for an extended period of time, you may need to go in and mechanically remove or chemically treat the shade intolerant mid-story. And with that, I'm all finished. Thank you all for listening and sticking around for this last talk.